In this lesson, we're going to look at drawing free body diagrams and writing Fnet equations for solving Newton's laws problems. Being able to draw a good diagram and writing the appropriate Fnet equations is a critical step in being able to problem solve in this unit. So first of all, let's look at a couple very simple diagrams. Our first diagram is just going to be something falling. We're not going to consider air resistance, so it's just like what we did in kinematics, where we had an object falling without the consideration of air resistance. As you already know, all of our diagrams are going to start out with a simple box. And then on the box, we draw forces, which are vectors, as arrows pointing in the direction that the force is applied. So we know that the force of gravity on a falling object is always going to be pointing down. So there it is. That's a diagram for the object that has a force of gravity acting on it, and it's falling due to the force of gravity. Now you'll notice one of the things I've done is when I draw the arrow, I always draw the arrow, tail of the arrow, starting at the box and pointing away. So all my arrows are always going to be pointing away from the box. No matter where the force is actually applied, the arrow on the box points away from the box. So let's add one thing to this. We're going to add air resistance. So here's my box. Here's my same force of gravity. Now we know that if air resistance acts on something falling, it's going to point in the opposite of the direction of motion. So there we go. Force of air, pointing in the opposite direction. You'll notice there's still nothing pointing left or right, because I don't have any forces in the left or right directions. Now let's draw a diagram of a box sitting on a desk. So here's a box sitting on a desk. Or we could even call it a cart sitting on one of our tracks, motionless. So just like the object that's falling, we still have force of gravity. However, there's a force that keeps it going through the track, keeping it stationary. We call that a normal force. A normal force is a force that's in the contact between two surfaces. So there we go. There's a box or cart sitting on a track, motionless. We could add a little bit to it. Let's say we have the same cart on a track. We have the force of gravity, always. We have a normal force. And then we're going to pull the cart to the right. So we'll just call that F. Here's the force pulling the cart to the right. Let's add one more thing. So we'll do the same thing. We'll draw our box. Now we're going to have, instead of a cart, we're going to have a box. This one's definitely going to be a box or a block or something. So we're going to have the force of gravity. We're going to have a normal force. We're going to have our pull to the right. And then we're going to consider the fact that there's some sort of friction force. Force of friction, or maybe it could be drag, could be some force that's resisting the motion. So friction and drag always act opposite of the direction of the motion. So the object's being pulled this way, so the friction is going to be pulling back to the left. There we go. That's pretty much every situation that we're going to encounter when we do a free body diagram. So now let's look at our net force diagrams. So now let's look at our net force equations. So in that forced equation, we could have up to two. We could have one in the vertical direction, or we could have one in the horizontal direction, or in some of these cases, we could have them in both directions. So let's first look at our top example. Now the way we write an Fnet equation is we just start with Fnet. In this case it's in the y direction, so I can put a y right there. All right, and that's going to always equal something. So we have to go back to Newton's first and second laws at this point. Newton's first law tells us if the body's at rest or constant velocity, the net force is going to be zero. So that's our first question. We write Fnet equals. Well, what does it equal? Okay. Well, we know that this object has unbalanced forces. The only force acting on it is gravity, so it's going to be accelerating. So in this situation, we would write Fy net equals mass times acceleration. We have to go to Newton's second law because Newton's second law tells us what's actually happening when it's either not at rest or not moving at a constant velocity. So here's our beginning place. Fnet equals ma. Well, what is Fnet? Well, if we look, Fnet is going to be 0 because we don't have a force going in the positive y minus force of gravity. So we have 0 minus force of gravity equals mass times acceleration. Let's go to our next example. Our next example has air resistance. Now there's two situations here. We could say that it's accelerating, or we could say that it's at constant velocity. So let's look at both. The first thing we'll do is we'll look at air resistance when it's at constant velocity. Or another air resistance, or when air resistance is involved and something's at constant velocity, we call that terminal velocity. So we'll look at this thing falling with terminal velocity. So we know that our net force equation, Fnet, equals 0 because we said it's at constant velocity. The next step in our problem is to write out what Fnet is. So Fnet is F air minus force of gravity equals 0. And the interesting thing about this is it tells us that the force of air resistance equals the force of gravity, which we should know because if the velocity is constant, the forces have to balance out. Now, if you'll notice, I used particular signs in this. The force of air was pointing up and the force of gravity is pointing down. We use our standard XY coordinates. So y pointing up is positive, y pointing down is negative. X pointing to the right is positive, X pointing to the left is negative. So let's look at when we're not at terminal velocity, when we have something that's actually accelerating. So we would still start out with Fnet equals, but it's not at constant velocity, so we would say it's mass times acceleration when it's not at constant velocity. So to solve that problem, we would write F air minus force of gravity equals ma. Now you'll have certain parameters in the problem and you have to plug them in appropriately to solve the problem. As you notice, for every single type of problem, we're going to have a unique set of equations or a unique equation for that problem. So I can't give you 10 or 15 different equations and have you try to figure out which equation to use to solve a problem. You have to be able to draw the diagram and write the equation that satisfies that set of conditions. All right, so now let's look at the book sitting on the desk or the cart on the ramp. Here we go again, Fnet. Well, if it's motionless, it equals 0. So we would go with F normal minus force of gravity equals 0. Another way of looking at this, we can always say Fnet equals mass times acceleration. Well, if it's at rest or constant velocity, acceleration goes to 0, which again brings us right back to Fnet equals 0. The next example, we're going to show the cart on the ramp, but we have a force pulling it to the right. We can see that the forces aren't balanced. So it's obvious that the net force in the y direction is 0, but the net force in the horizontal direction is going to be mass times acceleration. So let's take a look at this problem. We're going to have two Fnet equations. So our first one, we're going to write Fynet equals 0, and that's going to be Fn minus Fg equals 0. The second one is going to be Fxnet. So Fxnet equals mass times acceleration. And we could say that that's acceleration in the x. So we're going to have the same exact equation for Fnet, but instead of it being equal to 0, it's going to equal mass times acceleration. So we get Fn minus force of gravity. Whoops, my bad. We're talking about the x direction, so we're going to get just F. There's nothing on this side, so it's just F equals ma. Lastly, let's consider the same problem, but this time we're going to incorporate friction or some sort of drag force. So we're going to have an identical problem in the y direction. So we're going to have Fynet equals 0. So Fn minus force of gravity equals 0. In the horizontal direction, we're going to have Fxnet, equals, well, we don't know if it's constant velocity yet or actually accelerating. So if it were constant velocity, it would equal 0. Well, let's just assume that. It's moving at a constant velocity. So we'll say Fxnet is 0. So we'll say F minus the force of friction equals 0. Let's take the same problem and assume that it's accelerating. So in other words, Ff is a little bit smaller than F. So in this case, we'll write Fxnet equals mass times acceleration. So that's going to be back to the same thing though, F minus force of friction equals ma. So we've gone through 1, 2, 3, 4, 5 different free body diagrams and have shown you all the different Fnet equations. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 different equations that we could have actually come up with using these 5 different diagrams or 5 different situations. So you see, that's why it's so critical to be able to draw the diagram properly and then write the Fnet equations. If I were to try to give you a bunch of equations for every single problem that you might have to solve, you'd have a whole page of equations and you'd spend all of your time just trying to find what equation works. That doesn't work for this topic. We have to look at our diagram and have to be able to write an Fnet equation unique to each problem. Now lastly, let's spend a minute talking about this guy, force of gravity. So force of gravity can be given to you in 2 ways. If a problem says an object has a weight of 10 newtons, that is the force of gravity. Force of gravity, Fg, equals weight in newtons. Another way to express this force of gravity, or this object, is I could tell you that this is a 1 kilogram object. So if you're given the mass of the object, which is 1 kilogram, then you have to find the force of gravity. So force of gravity is equal to mass times the gravitational field strength. Well, on Earth, it's 9.8, which is the same thing as the acceleration due to gravity, or the free fall acceleration. So force of gravity for a 1 kilogram object would be 1 kilogram times 9.8, which would give me 9.8 newtons of force. Don't mix up mass with force. Force of gravity is the effect that the Earth's gravitational field has on an object with mass. Mass is a universal property of matter. So a 1 kilogram object anywhere in the universe is still 1 kilogram. The force that it might feel is the effect of the gravitational field on an object. So for example, if we take an object to the moon, the force of gravity is 1/6 that of what it is on the Earth, because the gravitational free fall acceleration on the moon is 1/6 that of the Earth. In the next tutorial, we'll look at how we actually use the Fnet equations to solve a problem.